Hello everyone, I would like to talk about the technical background of guide wave testing in pipeline. This is one of the main topics in this training. In this video, I would like to talk about what guide waves are, the background and the nature of guide wave inspection, how the guide wave testing compares to ordinary ultrasonic testings, the merit of guide wave testing, and an introduction to dispersion curve and particle displacement that defines the different wave modes. This schematic drawing shows the guide wave propagation in the pipe wall. Guide waves are ultrasonic waves that propagate along the length of a structure, guided by and confined in the geometric boundaries of the structure. The ultrasonic wave exists in medium and material, such as a pipe wall. Once it is generated, it propagates through the pipe wall. If there is anomaly in pipe wall, some of the waves will be reflected. This is the background of long-range guide wave inspection. It is introduced for field use in the late 1990s. There are two kinds of the guide wave probe. One is electromagnetic based, that is used with the MSS system. Another is piezoelectric based, that is used with the teletest and the wavemaker systems. The guide wave uses two kinds of wave modes for pipe inspection, torsional and longitudinal mode. The frequency range is between 10 kHz to 250 kHz. This slide explains the nature of guided waves. The guided waves exist in the many different forms: longitudinal, torsional, flexural in pipe structure, ram wave, shear horizontal wave in plate structure. The properties of guide waves such as velocity and displacement pattern vary significantly with the geometric shape and size of the structure and wave frequency. In contrast, bulk waves used in the conventional UT depend only on the structure's material such as modulus and density. What is the difference between ordinary ultrasonic testing and guide wave testing? The main difference is the operating frequency. The operating frequency of guide wave testing is between 10 kHz to 250 kHz, but that of ordinary ultrasonic testing is between 500 kHz to 10 MHz. With a similar velocity, the wavelength is much longer with guide wave testing. This slide shows two data plots of guide wave testing and ordinary ultrasonic testing. The only difference is x-axis unit, foot for guide wave testing, millimeter for ultrasonic testing. In other words, the guide wave testing method is one of the ultrasonic testing methods using low frequency. Therefore, each small section of guide wave testing data should be analyzed with the same physics and rigor used in the ordinary UT. Do you believe that you can differentiate A-scan data of ordinary UT from that of a small section of guide wave testing if x-axis scale is covered? Now, let us compare conventional UT and guide wave testing side by side. The main difference is the usage of the method, local spot inspection versus rapid surveying of large areas. Waves used testing are bulk waves, compressional, shear wave versus guide waves. Frequency range is 0.5 to 10 MHz versus under 250 kHz. Defect detection is small defects versus relatively large defects depending on the condition. Inspection range is within inches versus on the order of 1 to 500 feet. For most inspection, the inspection range of guide wave testing is about 100 foot along each direction of pipelines for above ground CUI pipeline for finding about 2% cross-section area defects. The main difference between guide wave testing and ordinary ultrasonic testing is coverage. The below schematic drawing shows the coverage difference. The guide wave testing uses two different probes of encircling probe and MSS sector probe. The encircling probe covers the whole pipe circumference so that the guide wave fills the whole cross-sectional area and propagates. The coverage is a whole pipeline within the inspection range that is shown with a red-colored area. The MSS sector probe covers the section of a pipe circumference so that the guide wave fills the probe-attached area and propagates. The coverage is the section of a pipe circumference along the pipeline within the inspection range that is shown with a red-colored area. The ordinary ultrasonic testing using flow detector or phase array systems covers only at or near the transducer position. As you can see, the coverage of one guide wave testing will be equivalent or more than the coverage of 100 ordinary UT inspection. The guide wave testing is sometimes called a volumetric inspection method because the coverage is a large volume of a pipeline. As shown in the schematic drawings, the coverage is a multiplication of a pipe cross-section area and inspection range. However, it is only valid if inspector reviews and analyzes the signal at each small section of a pipeline along the whole length of a pipeline and reports the findings with a per indication or section detail plots. Let us talk about the merits of guide wave testing compared to other NDT methods. One main merit is a large coverage, so that the guide wave testing method rapidly provides comprehensive condition information on large area of a structure. Because the guide wave testing method transmits ultrasonic waves in the tested structure for long distance, it does not need to move along the pipeline. It requires minimal preparation of insulation removal, scaffolding excavation, coating removal, etc. for probe installation. It inspects inaccessible area remotely. Guide wave testing method is a volumetric inspection method. If the guide wave testing is performed using multiple frequency operation, it does not miss defects because it is a volumetric method. Guide wave testing method pinpoints where to use quantitative follow-up and enhance overall inspection efficiency by reducing time and cost. This slide shows the dispersion curve of ultrasonic waves in bulk steel. The mathematical form of a wave equation is that velocity is a multiple of frequency and wavelength. Because three variables are in one equation, it has two independent variables. The dispersion curves are usually shown in the two variables of velocity and frequency as shown in this plot. The x-axis is frequency and the y-axis is group velocity of the wave. The ultrasonic waves in bulk steel are longitudinal wave and shear wave. The difference of two waves are particle displacement relative to wave propagation direction. The longitudinal wave has the particle displacement parallel to the wave propagation direction. The shear wave has a particle displacement perpendicular to wave propagation direction. These two waves have a constant velocity at any frequency, so that the plot of velocity is parallel to the x-axis. We call this kind of waves as a non-dispersive wave mode. Now let us talk about guiding modes in pipelines. As we know that wave modes are decided on by particle displacement, we need first to know what kind of particle displacement exists in pipeline. There are three particle displacement: radial displacement, axial displacement, and circumferential displacement. The wave propagation direction is along the pipe axis for guide wave testing of pipeline. This slide shows three guide wave modes in pipeline. They are torsional, longitudinal, and flexural wave modes. These wave modes are classified due to the particle displacement. The torsional mode has only circumferential particle displacement. The longitudinal mode has axial and radial particle displacement. The flexural mode has all three particle displacements of axial, radial, and circumferential displacement.